Hello, everybody. Let's go with some questions from reaction kinetics. So the goal of this video is to go over some free response type questions from a past exam. Okay, so let's start with this question over here. So given the reaction mechanism and the energy diagram, write the expression for the equilibrium constant Kc for the overall process. Let me take a screenshot. Okay, you write the equilibrium constant expression. Okay, and analyze how Kc changes as a function of temperature. Okay, by sketching the graph Kc versus temperature, and we had to justify our reasoning as well. Okay, now let's see. First of all, the overall process. So to get the overall process, we need to add the two steps up, and we cancel out the intermediates, and we're going to be left with Rn2 EQ and CO2 gas on the left-hand side of the arrow. And on the other side, we have R and H CO2 minus AQ plus H plus AQ. All right, that should be our overall reaction. And then the equilibrium constant expression should look something like this. K is equal to products over reactants. Products are NHCO2 minus concentration times H plus concentration over Rn is 2 EQ concentration times CO2 gas concentration. Okay, and then that's the equilibrium constant expression. And then we need to sketch the K versus temperature graph. To do that, we need to know how it behaves with the temperature. To do that, we need the delta H and delta S values for this reaction. So we, according to the energy diagram, we are going from a higher potential energy to lower potential energy. Here are my reactants, here are my products. Okay, therefore the potential energy or the enthalpy decreases, therefore delta H must be negative. Okay, so delta H is negative because potential energy decreases. Potential energy decreases when you go from reactants to products. Okay, and then so delta H decreases is justified, and then delta S is the change in entropy. So on the reactant side, we have a gas molecule, and on the product side, we don't have any gas molecules. That means we are going from higher entropy reactants to lower entropy products. Therefore, entropy decreases. Okay, so delta S is negative. Why? Why is delta S negative? Because we are going from higher entropy to lower entropy. Reactants have a higher entropy than the products. Let's write that. Reactants have a higher entropy because of the gas molecules. Okay, because of the gas molecules on the reactant side. Okay, so that should justify the change in entropy, the sign of change in entropy to be negative. Okay, and then if that is the case, we know that our delta H is negative and delta S is negative. Therefore, this is going to be a temperature dependent reaction because potential energy favors the products, but the entropy favors the reactants. Okay, as a result of that, this is going to be product favored only at low temperatures. Okay, therefore, the K versus temperature graph, this is K, and this is temperature, and this is the line of 1, should look like this. K should be greater than 1 at low temperatures. And at high temperatures, K is going to become less than 1, meaning it's going to be a reactant favored at high temperatures. Okay, so just for completion, we should justify the enthalpy change as well here so that we can make sure our graders see it. Delta H is negative because reactants, okay, reason is reactants have higher potential energy, meaning, so this is comparative, right? It's a relative. Higher means a relative term. Higher potential energy than the products according to the energy diagram. Higher potential energy according to the energy diagram. Okay. In a situation where energy diagram is not given to you, then we need to look at the bond strength to determine that. Okay, stronger bonds means lower potential energy. Weaker bonds means, on the other hand, higher potential energy. Okay. So anyway, that's what I would write. Okay, so the next question: derive the rate law for this reaction and clearly justify your reasoning. So, all right, here are the 2 steps: step 1 and step 2, and then use blue and green. So the step 1 activation energy is this much. Step 2 activation energy is only this much. So step 1 has a high activation energy. Therefore, step 1 is lower. Okay, it's lower because it has a high activation energy. Okay, I mean, to clearly justify our answers, so we need to remember to do that. So slower, pointing to high activation energy, should show the grader that you know what's going on. But to be on the safe side, I would write it out as well. Okay, anyway, now with that, we know that the rate of the overall reaction is determined by the first step, the slower step. Therefore, we can write the rate law for that. Rate law for the first step, that should be the rate law for the entire reaction. And rate is equal to the rate constant times RNH2 AQ times CO2 gas concentration. Okay, that should be the rate law for the entire reaction. Okay, and then to justify our answer, the rate determining step is the first step. Okay, give me a second. So we can write step 1 has a higher activation energy. Therefore, step 1 is the rate determining step. Okay, and therefore we shouldn't have write it, but let's write it anyway. The rate law for step 1 is the rate law for the entire reaction, for the overall reaction or entire reaction. All right, that is done. And then if you if the rate determining step was the second step, or the slower step was the second step, things would have been a little bit different, because we're going to have an intermediate in the rate law, which we're going to replace by going to the previous step and writing out the equilibrium constant expression. I feel like we should do something like that as well, but we'll do it sometime later. Okay, anyway, so that should be the answer for this particular question. Moving on. to the next question. All right, let's do this here. Okay. Same mechanism. Imagine that some students claim that when this reaction reaches equilibrium, the concentration of reactants is equal to the concentration of products. State whether you agree or disagree with their claim and justify your reasoning. So equilibrium does not mean the concentrations of reactants are equal to concentrations of the products. Okay, there might be situations like that where concentrations are equal, but equilibrium does not necessarily have to be like that. So I would say I'm going to disagree. I disagree. I disagree. So let's write that. Okay. So now we know that this is a temperature dependent reaction, right? And then the direction of the reaction is temperature dependent. Okay, and then we already determined that this is product favored only at low temperatures, because it has a lower it has a negative delta H value, because lower potential energy of the products. Okay, now what this means is at low temperatures, okay, so what this means is at low temperatures, the K is going to be greater than 1. Okay, K is going to be greater than 1. And then, so that means, so we know K is equal to product concentrations over reactant concentrations. Okay, if K is greater than 1, then this means its product concentration should be greater than the reactant concentration. Okay, so that should do it technically. Okay, that should clarify, that should justify why I disagree. But you know what, just let's keep going for a little bit. At high temperatures, K is going to be less than 1, meaning you're going to have more reactants than products. Okay, so that means we're going to have less products than reactants at high temperatures. Okay, and then K becomes only, okay, at the switching temperature, at the switching, okay, at that temperature only, K is going to be equal to 1. Only at switching temperature. Okay, only at switching temperatures. Therefore, this claim does not make any sense. I mean, if they say at switching temperature, the reactant concentration must be equal to the product concentrations, yeah, I mean, we can run with that. Okay, technically, because we had 2 reactants and 2 products, it should be the product of the 2 reactants and the product of the 2 product of the 2 product concentrations must be equal to each other at the switching temperature. But anyway, this is going to be the only time that's going to happen. Therefore, this statement is not valid. All right. Anyway, okay, moving on. The next question. Determine the half-life of this process. Clearly justify a procedure by explaining how you derive any quantities from the data. Okay, now let's see. Okay. Being reported following milliseconds. All right. So right now, I think the most straightforward way to do this is, I'm not going to say the easiest way. I would say the most straightforward way is to plot this data. Okay. So whenever you have concentration and time data, okay, you can just plot time and concentration versus time, natural log of concentration versus time, and and 1 over concentration versus time, and see which one is linear. And that should tell you the order with respect to that particular reactant. Okay, and once we have the order, and then we can get the half-life equation to determine the half-life. All right, anyway, so let's do this. All right, so this is time. Okay, and then let's see what we have. For time, we have 0, 10, 20, and 30. Okay, so one thing I immediately noticed was, so we're starting at 2 times 10 to the power of minus 2, right? Half of this concentration is around 1 times 10 to the power of minus 2, or 9.48 times 10 to the power of minus 3 is close to that. All right, so let me show you something, and then I'm going to go back and solve it quantitatively. So here we see that the concentration is half, right, when you go from 0 to 30. So it seems like it takes about 30 milliseconds. Yeah, 30 milliseconds. A half-life is going to be something close to 30 milliseconds. Okay, based on this. Okay, and then I see that when you go from 1.56, this is like, okay, so when you go from 1.56 to this value again, is about half of this concentration, right? Because half of 1.56 is 0.78, something like 0.78 in the power of minus 2. Is it right? Yeah, 7.78. Yeah, something like that. And then that is equal to 7.8 times 10 to the power of minus 3, which is closer to this. So it's around 30 milliseconds. I feel like it is less than, a little bit less than 30 milliseconds. So let's figure it out. So it seems like it doesn't matter what the initial concentration is, the half-life is gonna be around the same, and that is consistent with the first order reaction. But let's do this without speculating, because we have the data in front of us. We have concentration at time 0 is 2 times 10 to the power of minus 2, and then at 10 is 1.56 times 10 to the power of minus 2, and then at 20 is 1.22 times 10 to the power of minus 2, and at 30 it is 9.48 times 10 to the power of minus 3. All right, now I have the time and concentration data. I want measure log of CO2 concentration as well. I'm going to have list 3 with that. So I'm going to have N and that. All right, so my list 3 has measure log concentrations, and then in my list 4, I'm going to have 1 over concentration of CO2, and it should be equal to 1 divided by that. All right, now I have all the values. Now I'm going to plot concentration versus time first. All right. Okay, insert graph. Okay. And then it turns out for concentration versus time graph, the R squared value is around 0.988. Right now, I'm going to plot something else. Okay, I'm going to plot natural log of concentration versus time. When I plot that, I got an R squared value of 1 exactly. So that proves that is going to be first order reaction. And if you plot 1 over concentration versus time, the R squared was 0.987. So natural log concentration versus time is the linear, it is the linear graph here. Therefore, it tells me that this is going to be first order with respect to carbon dioxide. So we can, let me just show you what I have here. I'm going to draw. Actually, you can do this during the exam as well. Once you plot the graph, okay, you can draw this out. And you can say natural log CO2 concentration at time t. And this is time, okay? This is linear. I wish I could draw this a little bit better, but anyway, what I have is what I have. So this is linear. And then, therefore, okay, so let me indicate this, that the slope is negative 0.0249, and then this is in per time units, right? The time is in the x-axis, the slope is delta y over delta x, so therefore it should be per milliseconds. Okay, is the slope. And we know for these graphs, the slope is equal to negative rate constant. Therefore, rate constant is equal to 0.0249 per millisecond. Okay, so we got the rate constant. Okay, and then we're talking about the half-life. So really quickly, let's do the half-life. Okay, so we know the for sort of reactions, natural log concentration at time t is equal to minus kT plus natural log of the initial concentration. And then at half-life, at half-life, we can rewrite this saying this should be equal to the concentration is half of the initial concentration is equal to minus kT half plus natural log of initial concentration. Therefore, kT half is equal to ln initial concentration minus natural log of half of initial concentration. Okay, which is going to be natural log of 2, right? R naught divided by R naught divided by 2 is natural log of 2. Therefore, T half is natural log of 2 divided by rate constant. And then this value should be natural log of 2 is, I think, 0.69. Let me see. All right. Log of 2 is 0.693. 0.693 divided by 0.0249 per milliseconds. Therefore, half-life is, if you divide that, 0.0249. It's around 27.8. I think it's right. 27.8. 7.8 milliseconds is your half-life. All right, so we estimated that to be around 30 milliseconds before. So it is pretty close about to that. All right, so that's the half-life. We determined that. And then what we're going to do is we're going to move on to the next set of questions. Let's write them. Okay, calculate the time it would take for the this reaction in question 20 to reduce the concentration of CO2 to 9 times 10 to the power of -6 mole. Okay. Now again, so we determined that this is first order, right? This is the first thing. So this data set is first order. Or we know that we plotted the graph, and then we know it's first order. Okay. And then for the first order reaction, we know natural log of concentration at time t is equal to minus kT plus natural log of initial concentration. Okay. And then the question is how much time, calculate the time it would take. So we are given the initial concentration, which is 2 times 10 to the power of -2, and the final concentration, which is 9 times 10 to the power of -6 molar. And then we know K from the previous one. I should have written it down somewhere, but anyway, and then we can use that. Okay, so the rate constant from the previous one was 0.0249 per milliseconds. Okay, so we have that as well. All right, let's do this. Now, therefore, from this, we can rearrange to say the KT is equal to natural log of concentration, initial concentration minus natural log of the concentration at time t, and therefore t is equal to natural log of initial concentration divided by the concentration at time t. Divide this entire thing by rate constant. Okay, so now we just need to plug and chug. So do it here. T should be natural log of initial concentration is 2 times 10 to the power of -2, and then they're asking about concentrate about 9 times 10 to the power of -6. Okay, divide this whole thing by rate constant, which is 0.0249 per milliseconds. Okay, and let's do this. So take out your calculators, and then you do the natural log of, I'll write the entire thing for the moment. I did not simplify the exponents of 2, which is fine because we can use the calculator. Divide this by 9 times 10 to the power of -6. Right, it's around 7.71. And wait, we're not done yet. We need to divide this by the rate constant, which is 0.0249. 0.0249 to get the time. All right, so yeah, we should definitely double check these calculations. All right, so I got around 309.5. 309.5 milliseconds. Okay, because per milliseconds in the denominator, so it's going to go up at milliseconds as milliseconds. So therefore, this should be your answer. All right. Now, in that, let's move on to the next question. Imagine you catalyze this process. Draw on the graph how the data on the catalyzed process would compare to the uncatalyzed data shown. Clearly justify your reasoning. Okay, so draw on the graph. I don't think this is the graph they intended to have, but anyway, so okay, so the idea is if you have a catalyzed reaction, it's going to be faster. All right, so this is how I would think about it. Now, at any given, so we have 4 data points here, okay? So you see that at 0.00315, the rate constant is around around 4.3, right? So if it is catalyzed, then it should be higher than 4.3. And the same thing here. So, and at the next data point, right, at that particular temperature, rate constant must be higher, and then it should be higher and higher at this point as well. So if you plot that, so you would get something like that. Yeah. So I think that's all we can have there for that. And then I would have liked this to be a first order diagram, and it will be much nicer, but it's okay with L and K versus 1 over temperature as well, or any slot. All right, and justify your reasoning. So okay. Now it's all goes down to this. Okay. Now I need to look back just to be consistent here. So we know that rate constant is equal to A times e to the power of minus EA over RT. So at any given temperature, so for catalyzed reaction, what is going to happen is the activation energy is going to go down. All right. So the value of activation energy is going to go down for the catalyzed process. Okay. So let's write that. Catalyst decreases the activation energy. Okay. So we see that we have e to the power of a negative value, right? E to the power of minus activation energy. So when you bring down that value, the overall value of rate constant increases. Increases, right? When you bring the activation energy down, the rate constant value increases, okay, at any given temperature. So catalyst decreases the activation energy, which in turn increases the rate constant at any given temperature. Okay, as a result of that, K increases. Okay, therefore K is higher at a given temperature compared to the uncatalyzed reaction. Okay, so we can run with that. All right, moving on. I believe it's going to be the last question. All right, let's do the last question. Based on your analysis in question 16 through 22, I can remember that. Anyway, propose the best experimental conditions to sequester CO2. Sequester CO2 is the outcome of that reaction. So it's about making the reaction with soap more product favored. So that's going to be the reason. Okay. So the goal is to make the reaction more product favored. Okay. Thermodynamically, and then kinetically, the goal is to make the reaction faster. Okay. So if you can remember for this overall reaction, okay, sequester CO2 using aqueous solutions of amino acids to maximize the extent and the rate. All right, let's talk about the extent first. Extent. All right, extent wise, what we can do is to to make the reaction product favored. Okay. Okay. So extend. We need to decrease the temperature. Okay. To okay. Okay. Temperature must be decreased rather than that. Temperature must be decreased to favor product formation. Big, okay. Why? Formation because products have a lower potential energy. Because products have a lower potential energy. Okay, that's what we can do to do that. Okay, and then okay. Now the issue with that is, okay, when you lower the temperature, the rate of the reaction, so we have rate as well. Okay, rate is going to be adversely affected by that. Rate is going to slow down. Okay, but then the rate decrease in temperature. However, let's write that. Okay, let's write however, decreasing T decreases the reaction rate. Decreases the reaction rate. Okay. Therefore, we should add a catalyst. Just to have fun with it. We should add a catalyst while decreasing the temperature. Okay, so because we know the catalysts make the reactions go faster. Okay, yeah. So I think that's what I would do. That's how I would tackle these problems. I hope this helped, and I'll see you guys in class. Bye, everybody. See if I can go from here.